Here's the last topic of the semester is vector valued functions. It really starts out very easy. The first two sections are, well, the first section is fluff, and the second section is calculus definitions completely analogous to what you've already done. So I'm going to go through this opening stuff very quickly, and we'll do some more interesting applications next time. But a vector value function is just what it says. It's a function that if you put in something, you get out a vector. In particular, we're interested in putting in a number and getting out a vector at this point. We've already done that to a certain extent, right? We did parametric curves, and on parametric curves, you could write x as a function of t and y as a function of t. Let t run between 2 points like a and b, and sweep out a curve in the plane. What we want to do now is consider a vector, r of t. Here's r of t, a typical r of t. And maybe it goes from t equals a to t equals b, and the vector moves around, sweeping out these points in the curve with its terminal point. If we make r of t equal x of ti plus y of tj, the terminal point of r, since the r is at the origin, is x of t, y of t, and the terminal point sweeps out this curve. This is a more compact notation that's used extensively in physics and engineering and so forth. And so this is a nice way of writing curves that we call vector parametric form for C, as opposed to parametric equations. This is like Peter Piper picked a peck. As opposed to parametric equations of the curve. All right, so here's the vector whose terminal point sweeps out the curve then, and it starts at x of a, y of a, and it finishes at x of b, y of b. It's just new notation. See, I told you it's fluff. And we have these nice parameterizations that we can carry over the new notation, right? Before, we could make an equation of a line x that went through a point x0, y0 in the direction AB by letting x equal x0 plus AT, y equal y0 plus bt, and t be an arbitrary real number. This means t is an element of R, the set of all real numbers, is that notation. Here, R of t, similarly, you put what x was times I plus what y was times j, and now you've got it in the vector parametric form. And we could do line segments, remember, if we then just generalize this and say, well, to go from x0, y0 to x1, y1, we want to use the vector with components that are the difference of the coordinates of these 2 points. So we take x1 minus x0 for the first component of the vector from point 1 to point 2, or point 0 to point 1. And y1 minus y0, the difference in the y coordinates. And this with this are the components of a vector that goes from x0, y0 to x1, y1. So we just take x0 plus at, y0 plus bt, just like here, where a and b are just the difference in the coordinates of the 2 points. And now we let t go just from 0 to 1. And when t equals 0, you observe, right, that you get the point, this falls out and this falls out, you get the point x0, y0. When you put t equals 1, the x0's cancel, right, this is 1 times x0, and the y0's cancel, you get the point x1, y1, so you get the line segment. Another common one was a circle. If you took r cosine t, r sine t, this swept out a circle of radius r. Here I use the other notation instead of the ij notation, just to show you we use both. And if you let t go from 0 to 2 pi, right, trigonometry told you that t was the central angle from the unit circle, and then multiply that unit circle by r to get a circle of radius r. So here's a nice way to parameterize a circle. Although those are the most important cases, there are other cases too. Maybe I should erase this circle here. What if I wanted to do an ellipse? Remember how to do those? T is no longer the central angle except when you're along an axis. But if you put r of t equal a cosine t, b sine t, what you find out is that, I'll let x and y, x squared over a squared plus y squared over b squared is cosine squared plus sine squared, which is 1. This parameterization sweeps out an ellipse of semi-axes A and B. Since we recall this is the general equation or the standard equation for an ellipse with semi-axes A and B centered at the origin with the major axis in the x direction. So you use that for ellipses, and there are other things you can do too if you want to get a hyperbola, for instance. One way to do it is to let r of t equal a tangent t be secant t. And because tangent squared plus 1 equals secant squared is a Pythagorean identity, this actually sweeps out a branch on a hyperbola as t runs from minus infinity to infinity. And then you can put a minus on one of these to sweep out the other branch. There are others. I think these are the main ones we want to be able to do. And with this in tow, there's just basically this new notation for doing parametric curves. We've practically done the first section already. And we want to look at doing calculus with vector value functions. All right, well, maybe I should back up just a little for a second and look at the problems here quickly. Here's the kind of problems that we want to be able to do with this. Find the domain of R of t. That just means for what values of t do you use to sweep out the curve? Right, so you can put any number t in here. You can say the domain is minus infinity to infinity, but here you want the square root to be non-negative, so t has to be at least as big as minus a third. That would be the domain for this one. You can eliminate parameters just like you did previously. Describe the graph. What is this? If ever you have an a plus bti plus, x0 plus ati, y0 plus btj, and that's what this is, we just saw that's an equation for a line. So if you have a linear expression, x0 plus at, y0 plus bt for the components, then this is sweeping out a line. And if you restrict t, then you're sweeping out to a closed interval and you're sweeping out a closed line segment. What about this one here? This is in 3 dimensions. Now you can do this just as well in 3 dimensions. But if you think about it, 3i, that just means x is fixed at 3. Now, y and j are 2 cosine t and 2 sine t. That sweeps out a circle in the yz plane of radius 2 at the origin. So this is a circle in the plane x equals 3. Right, that's parallel to the yz plane of radius 2 that is centered at 3, 0, 3, 0, 0. So you can sketch this one. But those things about circles and lines will tell you how to draw a lot of this stuff. Now this one's a little different. If you ignore the minus 3i, because that just fixes you in the x equals minus 3 plane, in the yz plane you see z equals t and y equals 1 minus t squared. So what does that mean? If you think about it now, if z is t, y is 1 minus z squared, and so the equation for this curve in the yz plane is y equals 1 minus z squared is a parabola. You can sketch y equals 1 minus z squared, right? And let t be arbitrary, sweeps out the whole parabola. This is how we write parabolas typically in the plane, is we'll let one variable equal t, and the other variable equal at squared plus bt plus c, and sweep out a parabola. This one is an easy one to draw, and then it's within the x equals minus 3 plane parallel to the yz plane. So what you do to sketch number 14 here, let's get it up there if I can. Maybe not. Hunter's law again. There we go. All right. So if I want to draw that curve, I draw in the x equals minus 3 plane. Let's put it over here. XYZ plane of the board. And this is the point minus 3, 0, 0. And we think of axes within this plane. We want to sketch z equals, y equals 1 minus z squared. Within this, we call it y prime equals 1 minus z prime squared. We call this the y prime, z prime axis within the plane, x equals minus 3. Then, well, y equals z squared is the baby parabola up. Minus z squared is down, and if you add 1, it shifts it up 1. But it's the parabola y equals z squared turned upside down and lifted up 1 unit. So it goes through here. 1 unit above this point, it must be minus 3, 0, 1. And 1 unit over here, since it's y equals z squared, just turned upside down and shifted. So I move 1 left and get to this point, minus 3, minus 1, 0. And 1 unit right to get to this point right here, minus 3, 1, 0. So that's how you can sketch a lot of these curves, and the idea is a vector valued function can sweep out a curve in space in this nice compact form. Alright, by the way, cosh and sinh are another way of writing hyperbolas. Cosh squared plus sinh squared equals, cosh squared minus sinh squared equals 1 is the identity for these, and so if I look at number 25 here just briefly, here's 25. X equals 2 cosh t, y equals 2 sinh t. Since we didn't specify t, it's assumed it goes from minus infinity to infinity. What happens? Well, since, here's how you eliminate the parameter just by hook or by crook. You use all your algebra, usually, and try and eliminate the parameter. We notice that x over 2 squared is cosh squared t. We notice that y over 2 is sinh t, so y over 2 squared is sinh squared. And if we subtract these, we remember that cosh squared minus sinh squared is 1. We notice that all the points on this curve satisfy x over 2 squared minus y over 2 squared equals 1. This is a hyperbola with semi-axes 2. Not semi-axis, with a and b equal to 2. And so what you have is this kind of a curve. All right, remember the asymptotes are y equals plus or minus b over ax. Is y equals plus or minus x. This is y equals plus x. This is y equals minus x. Just from what we learned about hyperbolas. And this goes through 2 units out, right? X equals 2, y equals 0 is the point of this curve, so it's 2, 0. And there's another branch here at minus 2, 0, if I sketch the whole hyperbola. But this isn't actually the whole hyperbola. You notice that this is actually, cosh is always positive, right? It's 2 cosh is e to the t plus e to the minus t over 2. So this is always positive coordinates, e to the t plus e to the minus t. This, however, sweeps over all positive and negative coordinates. If the y coordinate is going between plus and minus infinity, but the x coordinate is restricted positive, what we're sweeping out is just this curve right here. And since this one goes to minus infinity, the y coordinate goes to minus infinity, and t goes to minus infinity, and the plus infinity as t goes to infinity, the curve is being swept out this direction. Sometimes we'll put these arrows on here to show which way the curve is going around. So we don't get this other branch of the hyperbola. This just shows that all the points are on the hyperbola. And then you have to argue that this goes from minus infinity to a plus infinity along this in a continuous way. you can say that this is actually the curve C being swept out by this parametric form. So they're pretty straightforward, but you have to think just a little, right? Get that to C this time. All right. Now we can look at vector calculus. That's the background for it. We want to be able now to generalize what we did in Calculus 1. This is real straightforward. I don't want to go into lots of details. If you go ahead and take real analysis later, you can do this in more detail. But we will simply say that the limit of a vector value function, x of t, y of t, and you can do this in higher dimensions too, we saw that one three-dimensional example there, is taken in this way, that the limit is equal to L if the limit of the length of R, the limit is equal to L if the limit of the difference between R and L norm is equal to 0. So that's the official definition. It looks like what we saw for functions of one variable, except the absolute value is now replaced with the norm or length of the vector. So if the limit of the length of the difference between R and L is equal to 0, where L is the vector limit, then we say the limit of R to L. Alright, now what that turns out to mean, if you finagle with this definition of length, it's not too hard to prove that the limit of a vector valued function exists if and only if the limit of its components exists. And so all you have to do to see if the limit exists is use calculus 1 and see if the limit of the three components exists. There's nothing more to it than that. I told you it's fluff in here. All right? But you want to see the definition so you know what you're doing. I hated taking physics courses where I did all these theorems. I didn't know why they worked, and so I never knew when I could use them and when I couldn't. And that was very frustrating. Fortunately, I was a math major and eventually figured it out. You have examples like this. What's the limit of this thing? Well, you just take the limit of t squared times I minus the limit of this times j plus the limit of this times k. And if you want the limit as t goes to 0, then you just, since these are all continuous functions, you can just plug in t equals 0 and get 0I j minus 2k. And there's a simple limit. You just, if it's limit of continuous components, then you plug in the numbers just like you did in Calculus 1. Now what about derivatives? Once we've defined a limit, we want to use it to define a derivative. What is it? We'll say the derivative is just like Calculus 1, except with vector-valued functions instead of scalar-valued functions, ordinary functions. So in Calculus 1, we said f prime of t was f of t plus h minus f of t all over h, limit as h goes to 0. Same thing here, except r is a vector. Now that we know what the limit of a vector-valued function is, we just give it the same form of the definition. We say r of t is differentiable if this limit exists. Alright, so look how straightforward that is. But now this geometric interpretation is very interesting. If you take, they've got a picture here somewhere. Maybe I should point this out too before we do the picture. All the theorems similar to Calculus 1 follow. The derivative of a constant vector is 0. The derivative of a the derivative of a constant, this is not a vector, right? Because a scalar multiplication, a number times the vector. The derivative of a number times a vector, you can pull the number out of the derivative. We're going to see another thing for when it's a vector, dot product with a vector coming up here. But a constant times a vector can be pulled out. The derivative of the sum of two vector-valued functions is the sum of the derivatives. And the same thing with the difference of the derivative vector-valued functions is the difference of the derivatives. And now if you have an ordinary function f of t times a vector-valued function r of t, it follows a product rule. F of t times derivative of r plus derivative f times r. It follows the product rule. It's just now this is the derivative vector-valued function. This is the derivative of an ordinary function, sometimes called a scalar valued function or scalar. All right, these are immediate consequences they point out. You just have to go back to the same old definition of limit. I'm not going to ask you to prove any of that stuff. The object is to be able to use it. Here's the vector parametric form of an equation for a line. R equals R0 plus T V0. That's the vector form of writing what we did before. R equals X0, Y0 plus T times AB. And here's an interesting thing that you can sketch. Now we can make some more exotic curves, a helix for instance. If you look in the XY plane, what is this? That's the unit circle, right? X equals cosine t, y equals sine t, has x squared plus y squared equals 1 is the unit circle. T is the polar angle if you think about the unit circle in trigonometry, right? X is the cosine of the polar angle, y is the sine of the polar angle. So this is sweeping out a circle in xy space. If you look down on the z-axis, you'll see you're sweeping out a circle. Well, z is arbitrary to this point. This says that what you're actually doing is you're restricted to being on the cylinder, the unit cylinder. And then I also want z equals t. How can I sketch that curve in 3 dimensions? This is where it gets more interesting. Let's sketch R of t equal cosine ti plus sine tj plus tk. Right? The projection in the xy plane is the unit circle we know from our previous work. That means that whatever curve this sweeps out in 3-dimensional space, the points are all going to line the unit cylinder. It's the extrusion of that unit circle in the xy plane. And now what happens to z as I move around with this polar angle on the unit circle in the xy plane, z is moving up equal to the polar angle. So I'm going up like this. We should draw this in another color. So as t increases, z is equal to t. I go up like this, and so I'm plotting on the z-axis the angle that I'm at in the xy plane, and you get this spring shape that we call a helix. So if you have r cosine t, r sine t, and a at plus b over here, you'll always get a helix. As long as this is a linear function of the polar angle, you wind up sweeping out a helix like that. We can draw the direction it's moving this way, right, as t increases. All right, so there's plotting a helix. As you can see, these vector valued functions are very important in 3-dimensional space for space curves. Alright, now if you put a constant vector plus t times v0, this gives you a vector that goes through the point at the end of r0, points in the direction of the vector v0, because this is your parametric equations for a line, if you let t go from minus infinity to infinity, just written in vector form. This is x0, y0, and this is AB here. Now, what's interesting then is if you take the derivative of r of t. Suppose you have a vector valued function, this one, and you take its derivative, and we call that derivative phi of t. This is significant because v turns out to be the velocity, right? It's the rate of change of x and the rate of change of y vector. If you sketch it, you'll find it's actually tangent to the curve. They've got a nice picture here I was looking for just a minute ago. I guess it was up here. Yeah. Here's r of t, a vector valued function that's sweeping out this curve with its endpoint. Here is r of t plus h, a small increment. I think t is time a lot of times. That's why we use parameter t. Doesn't have to be time. Then there's this little vector going between them, and as this h gets smaller and smaller, the vector here for a smooth curve starts to become closer and closer to tangent to the curve. But r prime doesn't become becomes smaller and smaller in length because you're also dividing it by h. So in general, you don't get a zero vector. You can, but not in general. But what you get is a vector whose direction points closer and closer to tangent. In the limit, it is tangent, but it's not the zero vector because it's division by h. What you get is that r prime comes out to be tangent to the curve r and in the direction of increasing t. You notice because of this picture here. So that's what r prime is. It's often called the tangent vector, but because it has its components are the derivatives of x and y, it's actually what in physics we define to be the velocity vector. So if this is my spacecraft moving along here, this is my velocity vector. It has the direction that I'm moving, and if you look at its length is the root sum square of x prime squared plus y prime squared. It's my total velocity. So that's the interpretation of the derivative. It's when it's not zero, it's along the direction of increasing t, tangent to the curve, and it's also called the velocity vector when t is time. All right, let's see, down here. So this curve here moving along a helix, I can take the derivative, and if I take the derivative of the vector cosine t sine t, I get minus sine t cosine t, 1 for the components. And so r prime at any point t0 is this vector, and that's the velocity vector. If you think of this, let's see, I guess it's pictured down below. This is me going up the Matterhorn at Disneyland or something, that little rocket sled ride that they have here. V is in the tangent vector. It shows the direction I'm moving at any time. And it points out like this. And at t equals pi, this will be my tangent to my position here. All right. Now what's interesting here, because we're late in the course and we lost a little time here, we'll just point out that it's not actually too hard to derive the product rule. If you have the derivative of a dot product of two functions, why would we call it the dot product? One reason is that it follows a product rule for derivatives. R1 times derivative of R2, the dot derivative of R2, plus derivative of R1 dot R2 is the derivative of the dot product. And similarly, the cross product follows the product rule. R1 cross product R2 plus derivative of R2 cross R1. So the scalar product, the dot product, and the cross product all have product rules, and they're easy to compute. Then we have this wonderful theorem. If you take a vector valued function that's constant length, if this has constant length, you dot product it with its derivative, you get 0 always. Here's the proof of it. The derivative of r dot r by the product rule we just got is r times dr dt plus dr dt dot r, which is twice, right, since you do the dot product in either or, it's twice r of t dot dr dt. But if r has constant length, we remember that r dot r is its length squared. This must be equal to 0, so 0 equals the derivative of the length squared when it has constant length equals twice r dot dr dt. That means r dot dr dt is 0. So it follows that for a vector of constant length, r dot dr dt. All right, well, my camera died again. So the next topic is talk about definite integrals of vector valued functions. We make a completely analogous definition that the definite integral from a to b of r of t of vector valued function is time. Time is the limit of the sum of r of tk star delta tk. Same kind of definition, except now this is a vector valued function instead of a scalar function. And what that amounts to, if you use this definition, is that the limit of a vector value, or the integral of a vector value function, is equal to the vector of integrals. You just have to integrate term by term, just like you took the derivative term by term. See how straightforward it is? It's all just what you'd absolutely do naturally. The integral of r of t, which is x of ti plus y of tj, is the integral of x of ti plus the integral of y of tj. It's just the integral of the sum is the sum of the integrals, essentially. Constant come out, you can just prove this from that definition. It's pretty straightforward. The integral of the sum is the sum of the integrals. The integral of the difference is the difference of the integrals. And you can do antiderivatives. The antiderivative of a vector valued function is the component by component antiderivatives of r plus an arbitrary constant vector. So the constant becomes a constant vector. And here's an example they put in here to integrate 2ti plus 3t squared j. It's absolutely straightforward. Just integrate 2t and get t squared plus an arbitrary constant. In this one, you integrate 3t squared and get t cubed plus an arbitrary constant in this one. What you have is just well, they wrote it, I would leave it like this almost, but they wrote it as this vector plus a constant vector times ij. So it's the vector whose components are the individual integrals plus an arbitrary constant vector at the end. All right. And the fundamental theorem of calculus carries over. You take the integral of the derivative and undo each other, and you get back the original vector valued function to within a constant. Right? All right. So here's, evaluate this definite integral. You just integrate 2t and get t squared. You integrate 3t squared and get t cubed. You multiply each by its appropriate component. Evaluate it from, plug in the 2 and 0 and take the difference. You get 4i plus 8j. Pretty straightforward. Now we want to try some problems in here. Let me put these up here that I already put on board. Suppose I want to evaluate, now that I have some vector calculus, right? We'll just say vector calculus is completely analogous to calculus 1, component by component, just with a few little new things to think about. If I want to take the limit of a vector valued function, what do? We take the limit component by component. This limit of this vector valued function exists if and only if the limit of each and every component exists. What's the limit of this one? Well, from calculus 1, since they have the same power as t goes to infinity, you just look at the quotient of the dominant terms is 2/5, and the limit of the first component is 2/5. Limit of the quotient of polynomials where the bottom one is bigger as t goes to infinity, the bottom goes to infinity, this one's finite, the limit is 0. So this vector valued function is just approaching the limit of the vector of limits of components, 2/5, 0. Suppose I want to know if a vector valued function is continuous. Well, we look at this, and this is at t equals 0 in particular. Remember, the exponential function is a continuous function, and so it'll be continuous at t equals 0. This is a polynomial, right? It'll be continuous at t equals 0. The secant function is continuous everywhere in its domain, which includes t equals 0. So these components are all continuous. Yes, this whole thing is continuous. The vector valued function is. How about this one? If you want to calculate the derivative, it's just calculus 1 component by component. You compute r prime of t equals derivative 2 cosine t is minus t sine t. That multiplies pi. Derivative 3 sine t is 3 cosine t. And so you just take the derivative component by component. But now here's where the additional twist comes through when you're doing the vector calculus. How do you sketch this stuff? Now we have to make a sketch in the plane where r of t sweeps out the n component. What does 2 cosine t I plus 3 sine t j represent? Remember, a cosine t, b sine t sweeps out an ellipse. And actually you can use a sine and b cosine. It just sweeps out the ellipse going in the other direction starting from the y-axis. So you can use sine here and cosine here. And you can also use cosine of kt and sine kt, if, and it will just go around k times for each 2 pi the t goes around. So you can do similar parametric descriptions of the ellipse. We'll just use this one, use T and A and B here is the easiest. So it has semi-axes 3 and 2, so it goes up to 3 here and down to minus 3 here, over to plus and minus 2 here, or the axes. So it sweeps around like this, and what you do when you draw these things is you're supposed to draw r prime of t at the point, at the corresponding value of t here. So at r equals pi over 6, what do I get? I can compute r of pi over 6 is 2 cosine pi over 6 I plus 3 sine pi over 6 j. And let's see, cosine pi over 6 is equal to square root 3 over 2, so 2 times square root 3 over 2 is square root 3, that multiplies I. Sine pi over 6 is a half, so this is plus 3 halves j. And we notice that r of pi over 6 is, so here's the angle pi over 6. It's not the angle pi over 6 quite, I'm sorry. Right, on the circle it is, but not on the ellipse. This is the point close to pi over 6. Square root 3 halves. And there's r of pi over 6 is this vector right here. When we compute r prime of pi over 6, we draw it at r of pi over 6. So r prime of pi over 6 is now minus 2 sine pi over 6 I plus 3 cosine pi over 6 j. Let's see, 2 times a half is 1 I. 3 times square root 3 over 2 is 3 square root 3 over 2 j. And there was a minus on here, it's minus 1I. So I go minus 1 this way, here, 3 square root 3 over 2 up here. It should look tangent to the ellipse. And there is r prime of pi over 6. We draw it at the point r of pi over 6. And you're thinking of like your spaceship going around here. When it's right here, this is its velocity vector drawn at its position, at the end of its position vector. RT is often called the position vector in the sciences. When t is time and r represents position, of course. All right. So there's how to do derivatives and sketch them. It's the concept of calculus 1, just a little different sketch. Then we call the length of r prime the velocity of the object that's traveling when t is time. R prime, also called v of t, is the velocity vector. The length of the velocity vector is the velocity of the object, or better, sometimes called the speed. All right. So that's what we were just doing here. How about this one? Find the equation of the line tangent to the graph if we have a graph like this. 4 cosine ti minus 3tj. Suppose I wanted to find a tangent line. We'll make this the last part. And you can go ahead and try some of these. The integrals are fairly straightforward. I think you just integrate component by component. But you want to at least have seen those. So here's r of t equals 4 cosine ti minus 3tj. Find the tangent line in the plane to this curve that's swept out parametrically by this vector parametric form. Find the tangent line at 2 minus pi. curve? Well, the tangent line has direction vector. What you do when you think of making a line in parametric form is you say, I remember I need a point and a direction vector. So what's a point? I already have it. This must be my x0, y0 in the parametric equations for a line. What's a direction? If I'm on a tangent line, it's the direction of r prime. So r prime is minus 4 sine t I minus 3j. And we want it to be tangent at this point 2 minus pi. We'll have to plug in t. What is t at this point? In order to get 2 for, well, we can figure it from either component. But in order to get 2 for the first component, well, actually, maybe we better use both of them. Minus 3 times t has to be equal to pi, minus pi, so t must be pi over 3. If this is really a point on the graph, then t has to be pi over 3 to match it. Then you can check this one will match also. Cosine of 8/2, and we'll get 2 here. All right, so what I have to do to find the directions, plug in t equals pi over 3, and I get minus 4 sine pi over 3 I minus 3j. The tangent vector, sine of pi over 3 being square root of 3 over 2 is minus 2 square root 3 I minus 3j. So this is about 1.732. So this is about minus 3.5 here, and this is minus 3. The x component is a little more negative than the y component. But this is your A, and this is your B, and you write the equations of the tangent line L, if you like, as r of t equals x0 plus ati plus y0 plus btj, and we use this a and b and that x0 and y0. We've got, let's see, 2 minus 2 square root 3 t I plus y0 was minus pi plus minus 3 j. And there, maybe I should call it r hat of t to distinguish it from this curve r of t. R hat of t is parametric, the vector parametric form for the tangent line. You can also write, if they ask you for parametric equations, you just say this is x of t and this is y of t. The parametric equations are x equals 2 minus 2 square root of 3t, y equals minus pi minus 3, t running from minus infinity to infinity to sweep out the whole line.